Welcome to today's paper reading. Today's paper is titled, Chain of Thought Reasoning Without Prompting. This paper was published on the AR14 preprint by Xuezhi Wang and Denny Zhou from Google DeepMind. Our study introduces a novel approach to enhancing the reasoning capabilities of large language models, LLMs, by exploring their ability to reason without specific prompting techniques. Instead of relying on conventional prompting methods, we focus on altering the decoding process of pre-trained LLMs. By investigating the top alternative tokens during decoding, we discovered that chain of thought, COT, reasoning paths are often inherent in these sequences. This method not only bypasses the need for prompt engineering but also allows us to evaluate the intrinsic reasoning abilities of LLMs. Our findings indicate that the presence of a COT in the decoding path is correlated with a higher confidence in the model's decoded answer, which effectively differentiates between COT and non-COT paths. Extensive empirical studies conducted on various reasoning benchmarks demonstrate that this COT decoding approach effectively elicits reasoning capabilities from language models, capabilities that were previously obscured by standard greedy decoding. Large language models, LLMs, have shown impressive performance on various reasoning benchmarks, often elicited through prompting techniques. However, these methods often incorporate task-specific human priors, making it challenging to assess the model's intrinsic reasoning abilities. In this work, we explore a different approach, eliciting chain of thought, COT, reasoning through simple decoding changes, without the need for prompting. By examining alternative top K tokens during decoding, we find that LLMs can naturally exhibit COT reasoning patterns. This method, referred to as COT decoding, not only bypasses the need for prompting but also reveals the model's inherent reasoning capabilities without human intervention. Our findings suggest that LLMs can reason effectively without prompting, challenging the common belief that such reasoning is inherently limited. Additionally, we observe that the model's confidence in its final answers increases when a COT reasoning path is present, leading to more reliable decoding paths and significant improvements in reasoning tasks. Figure 1 illustrates how pre-trained large language models, LLMs, can perform chain of thought, COT, reasoning without the need for specific prompting. By examining alternative top tokens during decoding, rather than just the top one greedy path, inherent COT reasoning paths are revealed. These paths often result in higher model confidence in the final answer, as indicated by darker shading in the figure. This method, known as COT decoding, effectively bypasses the need for prompting and allows for a more accurate assessment of the LLM's intrinsic reasoning capabilities. The study examines whether pre-trained language models inherently possess reasoning capabilities without explicit prompts. Using the Palm 2 large model, the authors compare greedy decoding, k equals 0, with alternative decoding paths, k greater than 0. They find that while greedy decoding often lacks a chain of thought, COT, path, alternative paths reveal natural COT reasoning. The COT decoding method is introduced to reliably extract these COT paths by measuring the model's confidence in the final answer, showing a significant correlation between the model's answer confidence and the presence of COT paths. Table 2 compares various methods for extracting chain of thought, COT, paths from the top 10 decoded paths. The results show that COT decoding significantly outperforms other methods, such as greedy decoding and length-normalized log-prog ranking, in terms of reliability and reasoning performance. Specifically, COT decoding achieves a 95% accuracy on the year parity task, demonstrating its effectiveness in extracting COT paths and enhancing the model's reasoning capabilities. Table 3 compares the performance of COT decoding and self-consistency methods without the use of COT prompts on the GSM-8K dataset. The results show that COT decoding with 10 paths achieves a significantly higher accuracy of 63.2%, compared to self-consistency with 10 paths at 40.6% and greedy decoding at 9.9%. This indicates that COT decoding effectively encourages diversity at the first decoding step, leading to better performance in unveiling the COT reasoning paths. Figure 2 illustrates the effect of considering alternative tokens at different decoding steps. It shows that branching early, such as at the first decoding step, significantly increases the diversity of possible paths. Conversely, branching at later stages is heavily influenced by previously generated tokens, The optimal branching point can vary depending on the specific task, demonstrating that mid-path branching can effectively yield correct chain of thought paths in certain tasks. The experimental setup involves using a standard QA format where the model is prompted with a question and asked to generate an answer. During decoding, the default setting uses =10 for the top tokens at the first decoding position, followed by greedy decoding. This setup allows for ablation studies to explore the impact of different values. The datasets used include GSM-8K and multiarith for mathematical reasoning, a year parity task for common sense reasoning, and symbolic reasoning tasks from Big Benchart. The models tested include Palm 2 at various scales, Mistral 7B, and Gemma 7B, both in their pre-trained and instruction-tuned forms. Table 4 highlights the effectiveness of decoding in enhancing language models' reasoning capabilities. It shows that while other decoding strategies like top case sampling, nucleus sampling, and beam search either marginally improve or even degrade performance compared to greedy decoding, decoding stands out by significantly boosting accuracy on the GSM-8K dataset from 9.9% to 25.1%. This table underscores the unique advantage of decoding in eliciting reasoning from language models. Figure 3 illustrates how decoding significantly enhances reasoning in multiple language models, including Palm 2, Mistral, and Gemma. This decoding strategy consistently improves accuracy across various reasoning tasks, sometimes achieving double or triple the performance compared to greedy decoding. Figure 4 illustrates how decoding significantly enhances reasoning performance across different model scales within the Palm 2 family. It shows that on the GSM-8K dataset, decoding consistently provides an absolute accuracy increase of 10 to 30%. Conversely, for the year parity task, the model's performance remains unchanged even with increased model sizes when using greedy decoding. However, decoding recovers reasoning paths, leading to near-perfect accuracy at larger scales. Additionally, decoding enables a pre-trained Palm 2 large model to achieve 63.2% accuracy, closely matching the performance of an instruction-tuned model at the same scale. Table 5 highlights the effectiveness of decoding on both pre-trained and instruction-tuned versions of the Mistral 7B model. Despite the instruction-tuning process already incorporating abundant COT annotations, decoding further improves the model's performance by encouraging more accurate reasoning paths. This enhancement is particularly notable in tasks like year parity, multiarith, and GSM-8K, where decoding leads to significant accuracy improvements. Figure 5 illustrates the impact of varying the value of, which represents the number of top alternative tokens considered, on the overall accuracy of reasoning tasks. The study reveals that higher values of generally lead to better model performance, indicating that correct chain of thought, COT, paths may exist but are frequently ranked lower during the model's decoding process. For instruction-tuned models, the effect of is less pronounced, suggesting that instruction tuning effectively promotes most COT paths to the initial decoding stages. Table 6 illustrates how a model's intrinsic reasoning ability is affected by varying task difficulty levels. The data shows that while decoding enhances reasoning performance across almost all tasks, the extent of improvement significantly depends on the task's complexity. Specifically, simpler tasks are more likely to produce correct reasoning paths. Additionally, the model's ability to generate correct COT paths diminishes as the number of steps in the reasoning process increases beyond 2. Table 7 demonstrates the significant improvement in reasoning performance when decoding is added on top of zero-shot prompting. This enhancement is evident across both models, with accuracy numbers calculated over the GSM-8K test set. The table highlights how this combination leverages the strengths of both methods to achieve superior results in complex reasoning tasks. The related work in enhancing the reasoning abilities of large language models primarily focuses on better prompting techniques to elicit chain of thought, COT, reasoning paths. These techniques often involve task-specific prompts and require manual prompt engineering, which can limit their generalizability. Recent advancements in COT generation include methods like step-by-step verification and self-evaluation guided beam search, which still rely on COT prompting. In contrast, our work explores the model's intrinsic ability to generate COT paths without explicit prompting. Additionally, existing decoding algorithms for language models emphasize fluency, coherence, and diversity, with less focus on reasoning tasks. Our approach differs by examining the decoding space on the token level and utilizing confidence scores, without the need for supplementary knowledge or additional models. In this study, the authors investigated the inherent capabilities of language models in generating chain-of-thought (COT) reasoning paths without specialized prompting. They found that exploring alternative top K tokens in the decoding space reveals the natural existence of reasoning paths within these models, contrary to the prevalent practice of exclusively employing greedy decoding. This exploration correlates with increased model confidence in decoding its final answer. Based on these findings, the authors introduced COT decoding to extract more reliable decoding paths, thereby enhancing the model's overall reasoning performance. However, this approach incurs additional computational costs. Future work could focus on leveraging these COT decoding paths to fine-tune models for better reasoning capabilities, especially in more open-ended answer scenarios. Additionally, the current exploration focuses on branching at the first token, but future research could explore branching at any token and searching for the best possible paths during the decoding phase, though this would substantially increase computational costs. Identifying the best token during the search remains an interesting and challenging direction for future exploration. Thank you for watching.